Hi everyone. In this video, you're going to learn about inverse functions. So let's start by looking at two functions. The first function is f of x, which equals 2x plus 1, and the second function is g of x, which equals x minus 1, all divided by 2. Okay, we are going to start by just filling out a table of values for f of x. So given x equals 3, 5, and 8, we're going to find f of x by just substituting or plugging in 3 for x. So for instance, f of 3 would equal 2 times 3 plus 1. That equals 7. F of 5 would equal 2 times 5 plus 1. That equals 11. And then f of 8 equals 2 times 8 plus 1. That equals 17. Okay, now what I'm going to do is I'm going to take the outputs for f of x, so 7, 11, and 17. I'm going to make those the inputs for g of x. Okay, so then I'm just going to plug these numbers into g of x. So if I find g of 7, I'll have 7 minus 1 divided by 2. That will equal 6 divided by 2, which equals 3. If I plug in 11, I get 11 minus 1 divided by 2. That equals 10 divided by 2, which equals 5. And then do the same thing with 17. 17 minus 1 equals 16 divided by 2. That equals 8. So I hope that you're noticing something here. When I took the outputs for f of x and I made them the inputs for g of x, I basically got the inputs for f of x. So the output for g of x is the input for f of x. When two functions have this property or this relationship, we call them inverse functions. Okay? So inverse functions switch the input and the output. All right, so that's the key thing I would say to remember about inverse functions. Inverse functions switch input and output, or you can think of it as switch x and y. Okay, let's talk about some notation. So the notation that we use to represent the inverse function looks like this. We would read that notation as the inverse of f of x. Now, sometimes this notation is a little confusing because it kind of looks like f of x is being raised to the negative 1 power, but that really is not what that notation means. In fact, this notation does not equal 1 over f of x, okay? And I just say that because it's easy to try to make that conclusion or that connection using properties of exponents. So don't look at that negative 1 as an exponent. Whenever you see that negative 1, think inverse, okay? Inverse function. So, like, knowing that f of x and g of x are inverse functions, we could say that g of x equals the inverse of f of x. Okay. Let's explore this idea a little bit more. Let's look at it from a graphical standpoint. So you know now that an inverse function switches the input and the output. So let's say f is some function. If the ordered pair a comma b is a point on the graph of f, then we know that the ordered pair b comma a is a point on the graph of its inverse. Okay, because remember, the inverse is just going to switch the input and the output. Okay. So I wanted to show you an example because there is another relationship graphically, another way that we can find the graph of the inverse. So let's just pick a function for f. I'm going to use one of our parent functions, and I'm going to use x cubed. So let's say we just start with a table of values. And I'm just going to pick some values for x. Let's use -2, -1, 0, 1, and 2. So if I plug these values into x cubed, I get -8, -1, 0, 1, and 8. So let's plot these points. -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. And here's our graph of x cubed. You should already know what that looks like because it is one of our parent functions. So the inverse, let's say I wanted to find the inverse or graph the inverse. All I have to do is take my table and switch the columns, switch the input and the output. So the ordered pairs on the graph of the inverse function would be -8, -2, -1, -1, 0, 0, 1, 1, and then 8, 2. Okay, so if I graph these points, -8, -2, -1, -1, 0, 0, 1, 1, and then 8, 2, I get a graph that looks like this. Okay, now, what I wanted you to see is that the graph of the inverse function is also a reflection of the graph of f across the line y equals x. This is y equals x, this diagonal line going through the origin. And so hopefully you can see the flip over that line. That is another relationship about the graphs of inverse functions. Graphically, if you graph the original function and its inverse, then you'll see a reflection over the line y equals x. Hopefully you recognize that graph as another one of our parent functions. The inverse of x cubed is the cubed root of x. So, you've been using inverse functions all along when you're solving equations. So, like when we say, how do you undo an x cubed? You cube root both sides. You basically are using inverses to undo each other. Okay. All right. Now, how do we find the inverse function algebraically? So, what if we're given an equation instead of a graph? Well, again, remember, it all boils down to switching x and y. So what we would do is first remove the function notation. So we'll just replace f of x with y, which we can do because remember they're equal. Then we'll just switch x and y, meaning we're going to write them in place of each other. And then we'll just solve for y. So I would subtract 1 on both sides and then divide by 2 on both sides. Okay, so we end up with y equaling x minus 1 divided by 2. And then we could replace y with our function notation for the inverse and say the inverse of f of x equals x minus 1 divided by 2. So guys, I wanted to show you that this is actually the function we started with in the beginning that I called g of x. And so that's exactly how you would find that inverse equation. You would just switch your x and y and then solve for y. Okay. All right, now, there is something called a one-to-one function. Now, in the beginning of this unit, you learned how to determine if a relation, which is just a set of ordered pairs, represents a function. And remember, what makes a relation a function is the rule for each input, you can only have one output. Okay? And so that meant, like if we were given a table of values, and we were trying to determine if the relation is a function, all we had to do is make sure that all of our inputs are different. Like it was okay if our outputs were the same, as long as our inputs are different. So this table does represent a function. It does follow the rule. For each input, there's only one output. But this is not a one-to-one function. A function is one-to-one if there is a one-to-one correspondence between x and y. So that means all your inputs have to be different and all your outputs have to be different. So that's what we mean by there's that one-to-one correspondence between the input and the output. So this would be an example of a one-to-one function. Now, why would we even be interested in this? Because if a function is one-to-one, then its inverse is also a function. Okay, because you can find the inverse of any equation, because all you have to do is switch x and y, solve for y, but that doesn't mean that the inverse that you find is a function, okay? So if you know that the original equation represents a one-to-one function, you already know the inverse is a function. All right, graphically, there is a test that we can do to determine one-to-one functions, and it's called the horizontal line test. Now, you might remember that we use the vertical line test to determine if a graph is a function, and so both of these graphs would pass the vertical line test. Okay, so both graphs are functions, but they're not both one-to-one functions. So if you do the horizontal line test, which says a function f is one-to-one if and only if no horizontal line intersects the graph of f more than once, then you can determine if it's one-to-one. So our first graph is not one-to-one because notice that the green horizontal line actually intersects the graph 3 times. The second graph does represent a one-to-one function because no matter where you draw a horizontal line, it will only intersect the graph 1 time. All right. So let's look at an example. Is f of x, which equals 5x squared minus 4, a one-to-one function? So if you're given an equation instead of a graph, since it's so easy just to apply that horizontal line test, I would just do a quick sketch of the graph of this function using the parent function and transformations. Okay, so in this case, the parent function is x squared. The graph is a parabola. The 5 is going to vertically stretch or narrow the parabola, and then the minus 4 is going to shift it down 4. So, I don't know, it might look something like this, just a quick sketch. All right, now I can tell, though, that the graph of a parabola will not pass the horizontal line test, because if I draw a horizontal line through that graph, it's going to intersect twice. So the answer is no. 5x squared minus 4 is not a one-to-one function. And in fact, quadratics in general are not one-to-one functions because their graph will always be a parabola and it will always fail the horizontal line test. Okay, now in a way that poses a problem because that means that the inverse is not a function. So how do we fix that problem? Well, often what we'll do is we'll find a domain for which the function is one-to-one. Sometimes we call this limiting the domain. So the idea is, okay, well, we just won't look at the entire graph. We'll just look at part of the graph. But you want to find part of the graph that will pass the horizontal line test. So here's one example. What if we limit our domain to x greater than or equal to 0? So that would be this portion of the graph of f of x. And the blue portion would pass the horizontal line test. Now, what would be the range for the blue graph? This is the domain. What is the range? Well, to find the range, I would just read the graph from bottom to top And so the range is y is greater than or equal to -4. You could also use interval notation for your domain and range. Okay, now you'll see why I had to find the range in a little bit. Since we have found a domain for which f of x is 1 to 1, we can now find the inverse of f of x. So I'm going to do that the way I know how. I'm going to switch my x and y, solve for y. So replace f of x with y. Switch x and y. Solve for y. So I would add 4 to both sides. Divide by 5. Okay, that leaves me with x plus 4 divided by 5 equals y squared. Now to undo the y squared, I'm going to square root both sides. Okay, now technically, when we square root both sides, we get two solutions, a positive square root and a negative square root. But since I limited the domain to x greater than or equal to 0, we would go with the positive square root. Okay? So the inverse of f of x, based on the domain being x greater than or equal to 0, would be the positive square root of x plus 4 divided by 5. Now, what's going to be the domain for the inverse function? Well, remember, inverse functions switch x and y. X is domain, y is range. So, to find the domain and range of an inverse function, you literally just switch them. Okay, so for instance, the domain of our inverse function is going to be x greater than or equal to -4. All I'm doing is changing that y to x. And the range is going to be y is greater than or equal to 0. Okay, now often we're more interested in the domain just because, the domain is limited there. All right, now, the other thing I wanted to share with you is I had another option. I could have limited the domain to x less than or equal to 0. Okay, let's just say that I picked the other half of the parabola, and I chose the domain x is less than or equal to 0. The green graph will pass the horizontal line test, so it is a one-to-one function. So I could then find my inverse function, switch x and y, solve for y. But what would be different when we get to this step here and we square root both sides? Instead of taking the positive square root, we would have taken the negative square root. Okay, so you do have options, sometimes when you're limiting that domain. But it might, like it did in this case, make a slight change when you find that inverse function. Okay, now, you guys, if we can put all of this together, we get a formal definition for inverse functions. So here it is. Given two one-to-one functions, f of x and g of x, if f of g of x equals x, and g of f of x equals x, then we say that f of x and g of x are inverses of each other. Okay, so what are we saying here? If f and g are both one-to-one functions, if we compose them, plug them into each other, if those two compositions both simplify to equal x, then we know for sure that those two functions are inverses. All right, here's an example. Show that f of x and g of x are inverses. So I just have to find these two compositions. We're going to start with f of g of x. Okay, so that means I'm going to substitute g of x in place of x in f of x. Okay, so in place of these two x's, I'm going to put 4 plus 5x divided by 2x minus 1. So at first it's going to look a little complicated, but then you should start simplifying. Okay. So, if in order to simplify this, I think in the denominator, well, we could probably just start with the numerator. We're going to have to find a common denominator. So, I'm going to have to multiply the 4 or 4 over 1 if you make a fraction by 2x minus 1, top and bottom. So we'll have 4 plus 5x over 2x minus 1 plus 4 times 2x minus 1 all over 2x minus 1. Okay. We're going to do a similar thing to the denominator, but before we do that, let's go ahead and multiply times 2. And so we'll end up getting 8 plus 10x all over 2x minus 1 minus 5. Okay, and actually I think I'm just going to go ahead and find my common denominator here as well. So we'll just do two things at once there. Okay, now that we have our common denominators, we'll just add our numerators. So I'll have 4 plus 5x, and if it's okay, I'm going to go ahead and distribute that 4. So I'll get plus 8x minus 4, okay, all over 2x minus 1. All right, and then in my denominator, I'll have 8 plus 10x minus 10x plus 5, all over 2x minus 1. Okay, we're getting there. Let's see what happens. Let's combine our like terms. Actually, I can tell that the 4s are going to add to 0. And then 5x plus 8x will give me 13x. All right, here the 10x and the negative 10x add to 0. 8 plus 5 is going to be 13 over 2x minus 1. And so now, if I multiply by the reciprocal, you're going to see some things reduce, cross-reduce. The x's cross-reduce. Excuse me. Ahead of myself. Let me write that again. If I multiply by the reciprocal, we will see some things cross-reduce. The 2x minus 1's cross-reduce and the 13's cross-reduce, and then it simplifies to equal x, which is what we wanted to happen. All right, you guys. Now we just got to go the other way. Okay, so we verified that f of g of x equals x. So now we just got to verify that g of f of x equals x. Okay, I'm going to put that in a different color. G of f of x. Okay, so now I'm going to flip that around. In place of both of these x's, I'm going to put x plus 4 divided by 2x minus 5. So here goes 4 plus 5 times x plus 4 over 2x minus 5. Okay, all divided by 2 times x plus 4 divided by 2x minus 5 minus 1. Okay, we will do a similar thing. I might start by distributing the 5 to get 5x plus 20. But since that's over 2x minus 5, I know I'm going to need a common denominator, so I'm going to end up having to multiply this 4 by 2x minus 5 as well. Okay, similar thing in the denominator, distribute the 2. And then I'm just going to convert the 1 to 2x minus 5 over itself. Again, so we have a common denominator. Okay, so now that we have common denominators, let's simplify our numerators. So I'm going to distribute this 4 now to the 2x minus 5. So that'll give me 8x minus 20 plus 5x plus 20. Okay, all over 2x minus 5. And then in my denominator, I'm going to end up having to distribute this negative. So I'll actually get 2x plus 8 minus 2x plus 5. Okay, we're getting there. Combine like terms, I get 13x over 2x minus 5 divided by 13 over 2x minus 5. And now we're going to multiply by the reciprocal, and you'll see a similar thing happen to where the 2x minus 5s are going to cross reduce, the 13s are going to cross reduce, and it's just going to equal x. Sorry, I ran out of room to show you guys, but I think you get the idea because we did the same thing in red. All right, so you guys, we showed that F and G are in fact inverses of each other by finding both compositions and showing that they both simplify to equal x. All right, so you guys, that wraps up inverse functions. We'll definitely practice this in class tomorrow, but just keep in mind that inverse functions, switch x and y, switch your input and your output. All right, as always, thanks for watching and have a good night.